Hold on. Hold on. There it is, stream manager. Run dev, hi. Welcome to the stream. I'm just waiting. Usually wait for a minute to start. That's enough time. Okay. When was last stream? Last stream was a couple days ago. So let me go over what I did between then and now. Okay, so this is here. Parser plus LIR. So I did do and break with unreachable blocks. So that's all. That's what I did today. This, and this. So, did I do this yesterday? No. Okay. So, let me go. This is a good context. Just put Discord over here. Alright, let's go to announcements. Alright, I posted all of these videos, and then here's some mass rewrite of the compiler, switch to a different intermediate representation, so the LIR. This is what I was doing. What did I do last stream? You know, I did IRs last stream, and now I've changed it a little bit. All right, so yeah, by doing data flow analysis, this is the old nodes. So node let decal, lambda, match, do block, loop, if, they all get trimmed down to this. And I removed a couple of these things because I changed it again. I changed the whole thing again to look and work a lot similar to Rust's MIR. Okay, and then here I did some of this, so valid transformation, this into this. But this wasn't the final product. Yeah, so I did, this is basically the initial thing that I did, even more of this, and then here, this is the most important part. Here, I'm slightly moving away from an SSA values type IR, integrating proper L values in the language, so it's more like Rust MIR. I'll explain what L values are and everything. It'll all look a certain way when it's done, I just need to implement it. The compiler would in theory be able to follow all paths to control whilst type checking to verify if something below would compile. Yeah, so that's just a different passes type check it takes. Okay. I can show you an updated version of this picture. Just all the way at the top. Alright. So 1. Type check. Uphold region assertion. So this one's easy. You can type check regions pretty easily. It's just when you pass them to functions, you need to make sure that they're right. Okay, assignments of region pointers and closures widen the type through unification. I talked on the Discord about how closure types work in my language. I'll talk about it when I get there, but I won't get there in a while, so I'm going to work through all of this. Okay, so 2, remove obvious dead code, basic blocks, like unreachable basic blocks, unwrap the unreachable keyword based on optimization levels. And then unwrapping, so I want to unwrap goto pattern, which was, I don't think I did it last stream, I don't know. But I talked about it. So unwrapping, make closures real. I unwrap vector operations, and I insert balance checking eagerly. Hocus Pocus 5 says, "How old is you, bro?" I'm like, I don't even know. I'm like 17. Yeah. Okay, SSA mem to reg, so I'm merging all of the address of operations, because when you take an address of a value, especially a stack value, it has an associated region, which means you can leverage the type system to align those rights. Yeah, okay, and then propagation of facts, range checking, language-specific optimizations, dead code elimination, region analysis, and lower. Let me just put conditional constant propagation. Anyway, this won't make much sense if you're not a compiler developer, but this is just here as reference. Okay, I'm gonna go over the output because it'd be better if I just show how it does. Okay, just go over and stop. Okay, I'm gonna assume that people have seen the last IR. I don't know. I forgot what I did on stream. LIR 10 initial LIR API. Okay, so I explained it a little bit in announcements, but the goto pattern abstraction is pretty easy to understand. Okay, so you have this function add, takes an i32, and then i32 returns an i32. So the add you're matching on A and B returns A plus B. A match with 0 equals A. 0 match with B equals B. And 0 match with 0 equals B. So, and then that makes sense. So the A and B will be exposed to the scope of this expression. Only the A will be exposed to the scope of this expression, and only the B will be exposed to the scope of this expression. And the 0, 0, nothing. Yes, you can see A, B, and A, B. They're in they're different indices, so they're different. Okay, so the entry block takes in 2 arguments because it's a 2-argument function. It constructs a tuple with them, so 2 equals 0 and 1, that's a tuple of. And this is how we do match expressions. This is match expressions before we, because we need to check if they're all exhaustive as well in the type checker. Yeah, so go to pattern 2. So it matches A, B, A0, 0, B, 0, 0. And you can see the basic blocks here, they have parameters. 0 and 1 for the entry block, 3 and 5, 8 and 10. So you can see matches on A and B goes to pattern this thing. So this is the first thing. The first pattern overload. So it takes in the parameter 3 and 5, so it reads so it writes 3 to A and 5 to B. And then 7 equals A plus B and writes 7. Zaka says, do you do some fancy SSA things? Yeah, eventually later on. It took a lot of time to come to the conclusion of like my current IR representation. I'm currently doing parsing right now, so it doesn't do any special IR stuff. Let me pause the music. Hold on. It's complicated. Yeah, it's so achieving proper analysis is really hard. Yeah. So you're right. So what I wrote like fully liveness, dead code, and everything. So this is I'm not gonna have an AST. So it's all gonna go straight into a control flow graph. That's basically my intermediate representation, the LIR, lowered IR. So without an AST, we have to generate the LIR from the parser, which means there's a loss of information. How do you keep all that information in there? How do you, because you don't want to unwrap a match expression into cases, into like if statements and matching, what is it? If they're, if you don't know they're exhaustive and stuff. So I use these specific abstractions. So this thing called goto pattern is a terminator of a basic block. It takes in an argument and a list of patterns. And then you just put all these patterns here, and they take block arguments. Those are like fine nodes. Simplifies a lot of things, and once the checker reaches this and verifies it, it'll unwrap this and use these parameters here. Yeah, so achieving proper analysis is hard, because I want to do constant propagation. Yeah, the parser outputs this IR right away. Yes, the parser outputs the IR right away. Everything that you see right here is straight from the parser. After doing type checking, it'll replace all of these and everything. Yeah, so this is more akin to a Rust MIR, but I've changed it to include SSA values as well. Yeah, so I want to do constant propagation, like conditional constant propagation. I want to do dead code elimination, language specific optimization. So I want to inline into a closure, constant values. I want to like propagate facts. So when I mean facts, I mean like the range of a value into other closures. Uh, this whole thing is it's very involved. It's very involved, and it's only possible with a complex IR like this one. So I'll explain its internals. It's the most important part. All right, all the way down to the bottom. Where is it? Okay. So yeah, GCC. Okay. So this function main.add, you can see it here. It's basically 4 patterns, 4 expressions. Okay, so you can see these are %0s and %1. Those look like SSA. I've made to make them look like SSA. Okay, so I'll explain. The whole every single instruction has a left-hand side. This will be an L value. So when I mean L values, I'll get into it. But essentially, they're like a local with a bunch of projections. So think field access and stuff like that. But currently they're just a bare L value. So it's just a local. Okay, so every left hand side has an L value, and that L value has to reference a local, and these are locals right here. A local in a function, so all functions have a bunch of locals. So all functions have a bunch of locals. This is the LIR local T. It has a type and a kind. So it has local underscore mut, which means can be assigned multiple times. Local immutable, which means can be assigned once in all flows of control, which means you can do this like what Rust does. Let v, and then if cond v equals 20, else v equals 50. But then you can also, I also want this to be possible as well. If not cond v equals 50. Rust cannot currently do this. Rust can't do this. In fact, it doesn't do this either. It can verify this is true. Yeah, so I want to be able to do this, right? If Rust can't do it, so I mean, someone's gonna try. So I want to be able to do this, and I think it's possible with the conditional constant propagation and everything. So this local mut and local immutable, these are generated by the user. So when someone goes let v or let tac v, this is an immutable, and this is a mutable. This is a mutable. Wait, that's an immutable, and that's a mutable. That's a mutable. Fuck. Anyway, you get what I mean. So local mut and local immutable, and then there's this thing here called local SSA. Assigned once. Block arguments can only be SSA locals. So what that means is this let v equals okay, let's do let v equals 50 plus 50. And there's a very good reason why I'm doing this local SSAs. So let's say %0 equals 50, %1 equals 50, %2 equals %0 plus %1. That's some SSA stuff, right? And then here you have v equals 2. Zaka says, you plan for variables to be uninitialized by default and eliminate invalid usage with analysis. No. So variables, you can choose whether or not you want to initialize a variable. Like the user can just put equals. But I'm going to eliminate invalid usage with analysis. Yeah, that's right. That's right. But even more analysis than Rust. The common approach people do is zero initialize. Yeah, but I mean like actually uninitialized data. So if I want a function to take a pointer to uninitialized data, I want it to write to the pointer, and I want to express that in the type system. Chat says hello. Hey, welcome back. All right, so as you can see here, it just says let v equals 50 plus 50. So SSA value 0 equals 50, SSA value 1 equals 50, SSA value 2 equals add them together, and V equals SSA value 2. And there's a reason why I make a distinction between SSA values and immutable values. It says here, semantically, SSA locals are constants. They can't have their address taken or assigned to. So you can have let's just assume 0 is a local, right? And I want to deref it and write to it. In the IR, it's expressed just like this. There is no load and store instructions. There is only left-hand side lvalues. Can't take an address of temporary makes sense, but it also is a nice abstraction for like the checker, because usually in the checker you would have a node tree, and you traverse that node tree and say, is this a valid assignable? Is this a valid L value? And it'll check, okay, this is a literal. You can't take a value of this literal. But I've effectively abstracted that away with the use of SSA temporaries. So the parser will generate these SSA temporaries here, and if you refer to 0, you're essentially referring to a constant. So you can't take the address of a temporary. Like, the checker will throw an error. So there's no need to walk back the expression tree. You just know for sure that 50 plus 50 is a constant that you can't take the value of. So it's fine if you don't get it, but this abstraction, the abstraction of making a distinction between SSA locals and immutable locals. So mutable and immutable are created by a user, and the local SSA are for constants, and they're inserted by the parser. Yeah. So, So this makes sense. I'll go and generate this thing. Yeah. So let me put this side by side. Yeah. So A plus B. So A4 equals 3, B equals 5, and then 7 equals A plus B. And if you try to take the address of that, you're essentially trying to take the address of 7, which is an L value to 7. 7 is an SSA local, which means you can't. It'll throw an error. I've tried doing this analysis on AST level, and there's no notion of temporary there. Well, you can well, how I did it in the last compiler is that it would just walk the tree and identify, because there's only a couple things that can be on the left-hand side. Field accesses and derefs, and then, like, array accesses. All you have to do is just check, do you have those? Anything else, throw an error, right? It's just like a tree walk all the way down. If you look in the old version of the compiler, which I used a tree stuff, you'll be able to see it. You know what? I can show you right now. A VOD saved anywhere. Yeah, they're all on my channel. But I can show you right now. Parser.c. Open timeline. Let me do a git stash. Actually, no, I'm not. I don't want to check git. Actually, I have an old one. I'm scared of git. All right, parser. C lvalue. C mute. Is it lvalue? Okay. This is what you do on the left-hand side. So yeah, can't take address of temporary. Yeah. So C lvalue. All it is I'll show you where it's called. In C assign. So you type check the left-hand side, and then you call C lvalue on the left-hand side. So you're checking if it's an L value. And then is mutable set to true because you're mutating it. And then here, node address of. So you're checking the node address of ref, and then you're calling CL lvalue on the ref. And then I'll show you how it works. All this is just you recurse down the tree. So switch on node.kind. If it's a variable, check if it's mutable, if that thing is set. But if it's a variable, you're done. You can just break. And then here, if it's a node deref, you can just check this, and if it's done, you just break. If you get things like a node field or something, you need to like recurse CL value on the other expression, or like the what's it called, the left-hand side or something. Anyway, yeah, so just call lvalue and then just recurse, and if it's not, you just go error. This expression is not an lvalue. That's the simplest way to do it, and that's how I do it in the node HIR. All right. Yeah, so this is malformed code, and I think I can show you what happens. It can be done, but IR allows to always be sure. Well, in all modern compilers, they can check the lvalue stuff on the AST. This is just a really nice abstraction. This is just a really nice abstraction. This notion of things, because SSA locals share the same. There's only 3 classes of locals: mutables, immutables, and SSAs, right? And SSAs share it, but they don't have a place in memory, so you can't take the address of it. They, for all intents and purposes, semantically, they're treated as constants. So you see here the address of a plus b, and then you can see here. So a b equals the parameters. 7 equals a plus b. 8 equals the address of 7, and then return 8. But you can't take the address of a SSA temporary. You know, it lets the parser know. It lets the type checker know that it's not a valid thing that you can take the address of, or a valid lvalue. Oh wow, yeah. See, these bugs right here: address sanitizers, segv on unknown address. The address sanitizer is supposed to tell you, but it's not telling me a thing. And when I run it again, it runs fine. So I'm pretty sure it's memory corruption, some undefined behavior. That's really annoying to track down, but I think, yeah, I've just not been caring the whole day. I just assume it fails every now and then. That's fine. I can fix that off stream. Okay. Well, another thing I need to explain. So I've explained basically the whole shtick of the IR. Yeah, I'll show some more things off. So I'll show you some lvalue stuff. Okay. Do you store debug info in IR instructions? Yeah, that's a good question. So when you mean debug, when I mean debug info, I mean like the position in a file. So there'd be two kinds of debug info. So there's a position in a file and like the original variable name. I store that. Yeah, I have a span in each expression. Yeah, so I'll show you what my my lock underscore t is comprised of: a u32 of the line number, a u32 of the column, a u32 of the pause, and a u16 of the length. That's the length of the whole token. What I should do is like merge spans together, so the location of a plus should comprise both sides, but I don't do that currently. That's like a to-do. But yeah, this is the lock t. So line number, column, position, length, and file. U32 start, U32 end is better. Yeah, it is better because it's like you can just when you report the error, you can just compute them, and if you have multiple errors, you can share them as well. Yeah, that's you know what? I'm gonna take that to do. All right, there, your name's in there, fully immortalized. Okay, yeah, so this is the location T. Yeah, everyone uses spans like that. Yeah, just like this lock T is copied from my work on the V compiler. That's how V did it, so that's just how I'm doing it as well. All right, so I'll show you how debug info was stored per instruction. Okay, so this is an instruction. It has its kinds, so it has a lvalue, so a destination, and just the list of tags, tag unions here. And there's no debug info in sight, so instructions don't store debug info. What stores debug info is locals. So all instructions have a left-hand side. All instructions have a left-hand side, which means a local to store to. And you can see here, lvalue, not here, LIR local t, they have a is debug info, location t, ISTER name, d debug info. Okay, and I'll explain. Yeah, each local is the expression of a value, but also you can assign to locals multiple times. So I wrote here, big LIR ambiguities. No, that's it's below, way below. Yeah, I wrote so much. I wrote something specifically about what you're asking, or what you're probably going to ask. Here, assign condition. So let v equals 20, v equals false. We actually don't store the location of assignment / individual instructions. We only store the left-hand side and the right-hand side as other lvalues or SSA locals. So I'm talking about locals, not the instructions. Should be fine, really, since the only error we raise is can't assign to this on the left-hand side. We all know SSA locals are semantically constants. So this here is changes to the percent. Is that right? Oh, mutable. Okay, this is mutable. So v, this. Okay, so v equals 20. Constant. Oh wait, hold on. Equals 20. Okay, yeah. So if you look at this, percent 20 equals percent 0 equals 20. V equals 0. So the checker can assume v has the type of an I32. And then percent 1 equals false, v equals percent 1. So the equals, so the equals right here, the equals instruction, you don't store the location of that. But what you do is you're referencing the local here, and you know the location of the local. So false will have location information here. Yeah, so they'll raise like a error. Yeah, so you have the right hand side. So that's all that matters, really. I mean, the temporaries can store the span of the expression on the right. Well, yeah, this is just my current. This is just my yeah. This is just my current thing. So yeah, I mean, makes sense. It's just assignments. It's just assignments. So you don't store the location of the plus. It's only stored in the where the value is getting assigned to. So these are locals. Okay. Now, let's see reassignments in action. So add sum takes 932, returns 932. Add sum matches on XS, so that's immutable, equals XS plus equals 20. So you can see XS 3 matches, and then here, this is the value of XS. XS gets stored to here. Percent 4 equals 20. Percent 5 equals XS plus 4. XS equals 5. Return 5. The semantics of the plus equals operator, I stole that from C. So it will evaluate to the computation. So this is basically being desugared to XS equals XS plus 20. And then the value of this side is being returned. And I'll show you how it's lowered, but you can see here that v4 equals 20, and then percent 5 equals XS plus 4, and then ret 5. So you can essentially remove this. You can remove this store. The optimizer can. But what you can't do is take the address of it, because it's an SSA local. That's another great thing about using SSA locals as an abstraction for values that you can't take the address of. Yeah, so the makes sense? Yeah, I think it makes sense. All right, and I'll show you the address. So it just reads it. Okay, just pretend it didn't exist. Good. So 1 equals tuple, and then here, this is the value of x in percent 2. X equals 2, %2, %4 equals the address of an L value containing x.3. %5 equals an L value of %4, and then you're dereferencing that L value in ret 5. So, how do L values work? I can show you. So let me just spam this, and then this 3 times. There you go. Run it again. Okay. And you can see I've composed all the .dref all into one thing. This is called an L value, and I'll show you how they're represented. So L values can appear on the left-hand side. L values always appear on the left-hand side. They always appear on the left-hand side. You can even do this. Expected pattern. Oh, wait. Yeah, I'll put this in a do block. Actually, equals this. Okay. Unexpected. Hold on. Wow. Okay. Yeah, so that's reading it and then writing it here and then returning this. Okay, this isn't a good example. But I'll just explain. So yeah, this is deref 3 times. Yes, it is derefing 3 times. So storing to 2 and then x.3. So this is in the local. I'm just appending the index. So it's deref, and then ret 4. And the reason why I'm packing them all together is because Rust does it. And well, it's not because just Rust does it. The reason why I'm packing this entire thing as one L value, not extracting it into a different instruction, is because of how it would work with regions. When you're performing, an L value like field accesses, let's say you have a struct, right? And you're performing a field access into something smaller. Another field access, another field access, another field access. You're accessing nested regions, which means if I have an L value that I can show you how it works, LIR L value, it's just an L value is a reference to a local, and then it contains a list of projections, and this list of projections can be deref, field, and index. So x.deref is local x is local x, and then an array of deref, which means it makes it really easy for the type checker to go, okay, this is the local, and these are projections, so I'm going to deref it again, which means I'm affecting the region bounded by this pointer, then this pointer, then this pointer, which means it all has to go from left and right. It's a really nice abstraction. Compressing all L values into one thing. It's really nice. It's really nice, especially for finding out what's on the left-hand side and the right-hand side. That's one of the big things that I was missing in my initial LIR implementation. So like the last stream and some work in between that, I think I came up with it all today and yesterday, the new implementation. So L values is really important. I can show you that Rust does it as well. Any other operations that stack like this? Okay, so deref field accesses, so tuple and named field access, and then let's say an index. So let's say you're doing like that. I haven't implemented that. I think I have not implemented that. Yeah. So this would compact down like that, and I think I can do a field access too, and then field. Unexpected field, expected top level statement. Wow. Yeah, okay, and you can see here x.3, x.3 deref, and then .0, because that's field 0. And here, let me go c equals do, and then c, let's see, deref equals 20. Okay, and then you can see here, c, deref equals %4, which is the 20. And I'll show you where L values get stored. Okay, so this is an instruction. It always has a destination, which is an L value. But if you have an instruction, inst lvalue, that means you're assigning an lvalue to an lvalue, basically. It's a copy. So, yeah, here, so this takes in a dlvalue. And then there's also address of, so it takes in an lvalue as well. There's many reasons why I chose this lvalue things. Having multiple things stacked together. Having those, having deref and field accesses stacked together. Because they can be on an assignment, the left-hand side, and they can also be on the right-hand side. There's many reasons. My original design, there's no way I was going to get that to have proper analysis. I mean, there's a reason why Rust models it that way. And I think I can show you where it is. Where is it? Here's our value. Or is it projection place? Okay, this is the implementation in Rust. So pub struct place, which is where is that from? Statement. Okay, statement. Oops. Yeah, so statement can be an assign which has a place and an R value. R value is essentially our SSA temporaries that we talk about before. But here, this is a place, so it contains a local and a list of projections. And that's essentially what Rust does, and that's functioning as well, because there's a ton of it just makes analysis easier. It makes analysis a lot easier. Yeah, so there's this notion of left-hand sides and right-hand sides. Okay, now let's get into specific things like branching. How do I do branching in this IR? Okay, go back all the way back. Okay. Now let's take the select function. All right. Takes in a bool, an I32 and an I32, returns an I32. So it matches cond A, B equals F. Yes, oh wait, F. If cond A, else B. Okay, simple. And then I run it. Okay, so this is where I leverage block parameters. So this if exit takes in a block parameter. So how it works is, this is the pattern, so this is the expression here. So I'm writing cond 5, I'm writing A, and I'm writing B. You can just ignore this, but so if cond, go to if then to, else go to if else. Yeah, so if then, you're gotoing, so you just go to if exit with the L value of A, so this value here. And then if else, you go to if exit with B here, the L value of B. So yeah. And then when you get to if exit, it takes in a SSA value, so you can't take the address of it. It's a local. It's a constant local, and then you can just return it. It makes some. This is just how I unwrap these these functional what is it? These functional semantics into something like this, right? Into a statement-based basic block things. Having fine nodes, having these block parameters make things a lot easier. But I mean, this makes sense. So if cond, go to if then, else if else. Yeah, so if then, go to if exit with A, and then if else, you go to if exit with B, and then ret 10. Now, if cond expr, right, an if expression with no else evaluates to void or the unit type. So how this is expressed is just like this. Let me bring this all the way up. Okay, so it takes in a cond and a so yeah, so if cond return A, but it doesn't return A, it returns the bottom type, so it ignores A. In the future compiler versions, it'll raise an error if you're ignoring a pure value, because if you're not performing any side effects, why ignore it? Okay, so you're just setting cond in A. So if cond, go to if then, else, go to if exit. So there's no if else. There's no like if else branch. So on the if then, you're just doing go to if exit. So there's supposed to be stuff in here. So let's just put like a do block, like yeah, we'll do like 3 plus 20, so it doesn't delete the operand. Okay, great. Okay, yeah, so it didn't delete the operand. So if then %7 equals 3, %8 equals 20, %9 equals %7 plus %8, and then you just go to an if exit. So this is just getting ignored. So an if exit returns here, if exit, and then %10 equals the empty tuple, and that's being returned. Pretty simple. All right, what I need to show you now is block expressions. So this is another functional thing that block expressions and the break keyword. Zeka says, is this IR not type check yet? No, not at all. You can see these infer types. These would be replaced with actual types. You can see these actual types here, but these are infer. These are not type check yet. I'm still writing the parser. So when I write the type checker, it'll be a very involved process. Not particularly. Just here, type check and uphold region assertions. That's fine. Remove obvious dead code. 1 and 2 would be pretty fine. Later you would emit typed IR. No, this IR is meant to be updated, to be typed. This IR is going to be typed eventually. I'm gonna run, so when it hits the checker, it'll type check the whole thing. All of these things will be assigned to types. Then it'll remove dead code. It'll unwrap and make closures real and assert bounds checks. SSA mem to reg. It'll propagate facts, conditional constant propagation, language-specific optimizations, dead code elimination, and region analysis. And then lower into probably C or a registered transfer language like GCC. Something. Like, I'll write my own kind of assembly. I think I'll need another representation. But I think I can just lower straight into C. For the first compiler, I can lower straight into C and be done. But yeah, this is all the type checker is doing. The type checker needs to do this because in number 5, it's performing some things. Yeah, I'm not an LLVM fan. I don't like it at all. Yeah, it's oh man, there's a reason why Zig wants to run away from it. I mean, Rust has issues with LLVM all the time. I mean, it's not even a stable thing to compile to. It's a big hunky piece of shit. Like it's so big. Yeah, I would never use it personally. I would either write my own code I would write my own code generator, and if I want something portable, if I want to be portable to multiple architectures to go compile basically everywhere, I'll just emit C at that point. Right? Imagine if I want to write some like embedded code, I'll just emit C. Yeah, so like programming languages use LLVM because I want to target everything. Well, if you want to target everything, you should emit like Gimple or something, or like a GCC. But I mean, in reality, why not just do C? Yeah, why not just do C? I feel like it's a pretty malleable representation. Yeah, so this is all comprised in the type checker. This is where errors can be raised. So this is your type checking. You're checking in a like an add expression. Is the left hand side type this, and like you're just checking like add expressions and things like that. And then here, you're checking is this variable assigned to in all the right spots? Is this value like it does data flow analysis. So like I said, it'll be conditional constant propagation plus the type system, which means that you'll be able to do this, like let v equals 2, and then let t equals array, mutable t. Then you can do t 0 v equals this, right? You can only do this with and imagine if that was conditional branches, but with constant propagation you'll be able to do this. T0v equals this, right? It'll be able to statically determine that is 2 elements on that side. So I'll need to do this thing: propagation of facts, range checking, conditional constant propagation, language-specific optimizations, dead code elimination, and region analysis. So I have to do all of these things. And so type checking happens in 2 stages. Type checking happens here. So that's a simple validation of everything. Then it removes all the dead code. Then it unwraps, makes closures real, vector operations, inserts bounds checks. SSA mem to reg here. And then this thing, propagation of facts. This is conditional constant propagation. So these bounds checks will be removed, elided. Things will be SSA'd properly. Dead code will be gone. It'll make sure that these constructs are possible. That's just the way I'm going to be type checking. So I'm integrating optimization with my type checker. This is something no language has ever done before. Rust can't even do this. And Rust is pretty good. Rust is pretty good with these like immutable rights and things. But you know, I always want I want to do stuff that no one's ever done before. Like if I was gonna ditch this project, if I'm just gonna make another imperative language that everyone's done before, I mean, why even start writing code in the first place? I want to write stuff that no one's done before. So this is what I'm doing. Yeah, Rust is much bigger. Yeah, but it doesn't implement all these. It doesn't implement all of these things, especially freedom with this, right? I mean, it would be so cool if you could do this. You can have slice lvalues. Rust doesn't have that. I wish it did. I don't use Rust, so it having it or not doesn't change anything. But you know, I want to do things that no one's done before, so that's why I'm adding all of this stuff. But in reality, it's definitely doable. I mean, I've weighed the odds a million times. Yeah, I can make this language really great. Okay, so let's do oh yeah, that's what happens when 500 people develop the code base. Yeah, yeah. All right. Okay, let's do blocks. So, let v. Actually, this has to be inside a main. Nothing to nothing, main. Equals do 15. Okay, this will obviously fail in type checking, but we'll be able to print it here. Run dev says, what's the main focus of the language? You know what? I've always wanted to write, so I write C all the time. Yeah, functional goodness. I write C all the time. Like, there's like, it's one of my favorite languages for a reason. There's many reasons why I like C. There's many reasons why other people like C. There's a reason why C hasn't died yet. So I want to bring all of these all the things that I like about C into a functional language. So because I've always liked functional languages and things like that. Especially closures. Like imagine if C had closures. Like C++ lambdas or something. Just simple closures like that are like really low cost. So a closure will essentially just be a function pointer with a pointer to its closure data. Yeah, so I mean, it's hard to write like modular code in C, right? Um, yeah, no, I'm not doing monads at all. There's no monads in this. Only effects, right? But if you perform an effect, like you usually think of effects like a monadic effect, but uh, yeah. So yeah, you usually think of like memory effects as like a monadic effect, but there's just no effects. Just a function can emit an effect, but it's just no monad stuff. Someone said something wrong with monads. Monads are nice. I mean they're pretty nice. The average programmer who doesn't know about monads probably uses them, like the option types and result types. I didn't know those were actually monads until I got to using them. Like I went to the Wikipedia page. Anyway, the reason why I'm not including monads in this language is because that requires like this language is functional, right? This language is functional as a impure functional language can get. But I'm not it's not like cuz how Haskell implements monads. It it puts everything into this simply typed lambda calculus, and it does all of these things and just removes monads because monads like the IO monads, like they're used for sequencing. things. The thing is, there's too high of a cost and implementation effort to add monads. I mean, I can add monads. I can add monads like later on. You know, it just requires heavy generics. I'm not doing. I don't want to deal with that right now. I don't want to deal with that right now. So to use the language like printing and stuff, you don't need to know anything about a monad. That's what I want to add. That's the reason. That's the whole point of this language. You want to make your own you want to make your own monads. You can go ahead. When I get generics in, but if you want to print something, you don't need to know about a monad. If you want to print, like let's say like print, all it does is just an IO right here, an IO effect, an IO effect. All functions are pure by default. But if you put IO here, that's an IO effect. And imagine you affect the global, right? You affect the global outside world, so it'll do like an effect on globals and things like that. We'll have something like option and result. Yeah, so it'll be like zig and v's option and result. So there is no like option t or option t here. There will only be question mark t, right? Because I like it's much shorter. Question mark t is way shorter. That's why I prefer it. There'll be question mark t, and then there'll also be the none keyword. None just means none. There's nothing there. There's a reason why I'm making none and result built in, because that means I can do like some like special type unification things. Built in instead of generics. Yeah, built in instead of generics. W Gaffer says, is this something like the research languages I've seen with effects like Coca? Oh, I really like Coca. I've seen Coca. So this whole effect system is going to work with the region system in my programming language. Let's say you have a mutable v, right, and you're mutating v. So yeah, all locals have their own region in memory, and that's with a region tag. And let's say you want to do a function mut this, which takes in a mutable i32, so a pointer to a tac i32. Tac means mutable. And then returns nothing, right? And the implementation is unimportant. So I'm going to call mut this with v and v. So it's the address of tac v, which means a mutable address of instead of address of mut, like in Rust. Yeah, so this is invalid code. It'll throw an error because this is a pointer and this is a pointer. By default, these two are in different regions of memory. So I talked about aliasing in a previous video. It's one of my videos that I turned into short form content. It's about how in this programming language everything is going to be non-aliasing by default. So let's say mut this affects a global, right? This is just some like I haven't decided on the syntax yet, but just assume that it has an IO effect on a global, right? And then I take the address of a mutable global. This is malformed as well because you're essentially having a region parameter into this as well, and these can't alias. You'll be able to assign a region like I don't know, like this 0 and this 0. So these okay. Now this is okay code. Yeah, region. This is 0. Anyway, the effects in this language is going to encompass two things. Effects on IO, like printing, they obviously can't be reordered, so it's just an IO keyword. But if you're writing to memory, it's more fine-grained. So you're writing to specific regions of memory. It's like Rust's lifetimes, but for regions of memory. I just wanted to elevate the current C aliasing rules. So you can have like address of question mark, which means this performs a C semantics aliasing, right? So if you call mut this, which it means like it'll perform an IO effect on basically like any pointer. So this is when you want to fall back to C aliasing semantics. So you need to reload all your variables after mut this. So all it is just effects on memory and effects on IO. So you can just you can't reorder IO. And you also know for sure which regions you're being written to. It's just like a pretty fine-grained like effect system. It's not like Coca. It's it's just like lifetimes and printing. Pretty simple, but it gets the job done, especially if you're writing a intensive an intensive thing like C, like a C program. I'm modeling this language off what I try to get done in C. Make things easier. Because this language is going to be my C replacement. And leading into RunDev's question, are you aiming for self-hosting the language? Yes. So initially, when I first finish this compiler, it'll be like the first release of the compiler. I only consider a compiler done when it's self-hosted. So that's just how I like to do things. I always self-host my compilers. I only consider it done when it's self-hosted. So how I'm going to self-host the compiler is through C initially. So I'm going to generate C. Like highly optimized C, it's highly annotated C as well. So there's specific like attributes, like I'm going to use attribute const, attribute pure, and stuff like that. Yeah. So so my initial release of the compiler, when I'm going to release it and it's going to be bootstrapped, it's going to generate C, and then later on I can do WASM because that's pretty easy, and eventually I want to do firmware. So I might write a x86, not x86. I might do a RISC-V, RISC-V 32-bit and 64-bit backend, and I can self-host from there. So when you say self-host, other people need to self-host it as well. So how are people going to get the compiler if they don't have the compiler for your language? So what I'm going to do is I'm going to store a C file in the Git repo, so you can build the compiler with just the C compiler, and that's easy bootstrapping as well. Yeah. So self-hosting is just going to be done with C. I think did I explain? So I didn't explain do blocks yet. So I was going to explain do blocks. I got carried away. Okay. Okay, let's just assume this returns an f32. Okay. Now you can see here, main, nothing in i32, main match on nothing, tuple, equals do block with 50. So, what happens is when you run it, all it does is 2 equals 50, return 2. It's pretty simple. You can do 60, 20, 70, clear, and the last expression will be returned. So 50, 60, 20, 70, and return 5. Simple. Pretty simple, but where it gets hard, let me just do that here. Yeah, so where it gets hard is with control flow. So this is going to be like Zig as well. These so I use goto in C all the time. I think I have a couple uses of goto in this compiler. There's a couple reasons why I really like goto. Not for the reasons that people assume. People use it's for the same reasons people use goto in the Linux kernel, right? You shouldn't be afraid of it. You shouldn't be afraid of goto. But it's how I really like goto, how I really like a replacement to goto is with Zig. So I don't know if you've seen Zig, but you can attach labels to blocks, and you can like break out of a block early. So you can just break label 50. This is exactly like Zig. Now I don't know if Zig has the break keyword as a statement or an expression. Zig break keyword. Zig break keyword. Break. Yeah, Rust is something similar. Yep, that's right. But isn't an expression blocks? What is this? What is this inside? Blocks. Okay, I don't know if break is an expression or not, but here. Okay, well, I wanted to go the functional route. So this break expression means divergent control flow, which means it'll evaluate to the bottom type, which is the no return type. It's no return in Zig, and the bottom type in it's called the bottom type because it's It's like the bottom of all the types. Anyway, you can't construct a value of this type. Run dev says Zig leans into annotating code blocks you can break with whatever you want to break. Yeah, that's what I want in this language. So named blocks, say like loop, having these named thing here, it's such a nice replacement for it's such a nice replacement for goto. So if you want to replace goto with keeping all of the benefits of goto but removing all the bad things of goto, it's annotated blocks right here. Annotated blocks, and then you can break out of blocks. It's super nice. All right, so you can look here. Exclamation mark is no return type. So if you want to, you can store the value of break. Here, v is the no return type to break, which means what the no return type means is that you will never be able to inspect the value of no return. Yeah, it does make code flow really clear. Yeah, so you will never be able to read the return. You will never be able to read the value of v because you'll already be out of the block. So the best way to explain it is just to show it. Okay, I don't have let in my language yet. Wow, I should get let. I'll do let this stream. Okay. Now, as I explained how do blocks work is you can break to the end. So I'm showing right now, you can break to the end. And also the value of the last expression in the do block will also be broken to the end, will be breaking to the end. So this will jump to here and return it, and this will jump to here and return it. So let me show you on the side. Okay, so this is the entry. Go to do entry. So this is right here. We're going into the do entry. 3 equals 50. So this is %3 equals 50. And then go exit with %3. And then do exit takes in %2 and then returns 2. So all it is 50 goes to do exit, and do exit returns 50. But there's a thing here. BRK actually evaluates to a value. So to get its value, you need to construct a no return type. How do you construct a no return type? You can only construct a no return type through unreachable control flow. So I create a new block which has %4, and that's this is our no return value. So the return value of do is an i32 and a no return type, which would be unified into i32. So there's so it'll return with an i32 and return with a no return type, and then the checker will be able to align this. Super easy. It's much better than this is much nicer and actually more reasonable than the HIR like tree IR, right? Yeah, so you're returning the value of BRK, and you're also returning this to here. So it's a no return and 50. And to constructing the value of a no return, which means you need a basic block that never gets touched, and then you can construct this value here, and that's the checker can check all of this. Run dev says, how are you handling or intending to handle errors? Well, for one, errors as values. So I don't think I'm gonna do it how Zig does it, where you can't the errors that Zig has, you can't attach values to. You can't attach like an error code. So I'm gonna do it like Rust and V, where you can specify like what error you want to return. So it can be like either error or value. So that's handling errors. But what I also want to do is I want to so I use set jump. I use set jump and long jump in C. Like I just use it because it's very fast. And what I want to do is, let's say you have an error and you want to unwind equals v2 unwinds and I want to unwind with t, right? So parser. Let's say I'm running the parser and I return something, and then there's a syntax error. I can unwind all the way back to the root. So this is my own kind of automated set jump implementation. I'm not going to go over it completely here, but what I want is I want all of these C constructs like gotos. I'm going to make these block expressions, and then set jump and long jump. I'm going to make these specific unwinding, like a specific type thing on unwind. I'm adding that as well. It's just this is going to be my C replacement. So I'm going to make this the best language it can be. Because eventually, the reason why I decided to make this language is because I was going to write firmware for a music player. Then I realized that I'm not going to be able to finish both, so I can only choose one. So I chose this to finish, and then maybe in a year, I'll work on my music player when I have this language done. The reason why I say in a year is because in a couple weeks, I have HSC and HSC in Australia, which that means like the big exam. So I'm going to be 18 next year. I'm going to be a full-on adult, which means I got to focus on my studies between now and then. So I only have so much time to work on the compiler, and then in another year I can work on it again. So I'm just going to try and get as much as I can done so my holidays end. Okay. Well, this explains breaking. So let me just spam this a million times, and I'll show you the output of that. Let me just do it twice. Thank you. Okay. Yeah, so, I mean, there's two break, Zaka says, would dynamic arrays / maps need to also be built in? Okay, so I said on the server, and I also said, I wrote in my personal notes, and I think I said out loud, my whole motto with this language is the whole language is available without dynamic memory allocation. You don't need memory allocation to use the language. So, there's going to be things like, so closures don't require dynamic memory allocation, so you can use them without dynamic memory allocation. So dynamic arrays, they can't be in the language. But maps though, maps can't be in the language like the ones that you can append to. But frozen sets, like let's say you have like a const, like a lookup, like a look up something, and then something you just is this, right? I want the compiler to look at this and make a perfect hash. I want the compiler to look at this and make a perfect hash, like a perfect hash lookup. Yeah, because that's one thing the compiler can help out on without using dynamic memory allocation. And a thing in programming languages that's like not really built in. I mean, I wish programming languages had like a like you could define a constant map, and then make the compiler just create a perfect hash for it, no memory allocation needed. So I can use that as like you can use that to like match on like you can use this to like, let's say like I'm doing a parser and I want to match on certain things. I think I'll just do like get and then something. Yeah, so I want this to be optimized by the compiler. Pretend this is a constant, and then I want the compiler to optimize this. This would be really good, especially because I don't need to do the work like optimizing. The compiler knows better. So if I'm going to rewrite the compiler, I want the compiler to choose the perfect hash, like the perfect hash table for this, and I can just do a perfect lookup. I can just do a lookup. Yeah, like if I'm writing a parser or something. That's the closest I've heard to that is comp time variables in Zig, I think. I think you can use Zig to make a perfect hash table. Zaka says, I can't imagine not having dynamic allocations. No, there's just not going to be any built-in. Like any built-in language primitives that need dynamic allocation, they're just not going to be built in. So you can have dynamic allocation like vectors, but you just got to import them. They'll be in a standard library. Now, okay, there's also a reason why I don't want dynamic memory allocation in my language by default. The reason why I made this language, as I said before, I want it to be for a music player, and obviously that's a freestanding target. That's a very freestanding target. And I wrote a lot. I wrote a lot around my whole language being this freestanding thing, and you can import things whenever you want. So I even wrote here. Yeah. So entry CPU, you can like write the CPU that you want, like vector, and then things like that. Anyway, in short, the whole language by default is freestanding. If you want specific things like here, you have to do like you have to go like this, imports. Yeah, you have to import runtime.libc, and then inside runtime.libc, it'll do a cyclic dependency on main. So that means there's no built-in entry points. So main doesn't become special anymore. The only reason why it's named main is because when you import a runtime, this runtime will do a cyclic import main and do a type assertion and then call it. Basically, what I'm trying to say is this whole language is going to be freestanding by default. Completely freestanding. Everything is going to be opt-in. You opt into everything. So if you want dynamic memory allocation, you need to get an allocator. You need to import one. That allocator might depend on a runtime. That runtime might need it might need to call like mmap or something. Like a runtime might expose like a page allocator or everything is going to be opt-in. I want the whole thing to be opt-in. So no dynamic memory allocation at all. All right. Now, what I was trying to say is these two breaks evaluate to exclamation mark. You need to produce them in two different things. So it does it here. Here L4 and L5. So these are the two calls. I think. Where is that? Huh. Let me think. Equals 50 goes to do exit. And that goes to do exit. And L5 goes to do exit. Is that by default? Trying to figure out. That makes sense. Anyway, that's just blocks. I think I explained blocks pretty well. I'll go to the code where I convert. It's called p parser expression. All right. Okay. There's my precedence climber parser, p identifier, p statement, p do blocks. Yeah. So all do blocks do is if it has a label, construct new basic blocks, perform like terminators, so connect the blocks together. Yep, create a new argument because that's the return. That's the return branch. And then in here, if there's nothing, create a tuple unit. That's the last expression value. And yeah, simple. Can you color the printed IR for long-term time savings? Oh, you mean like adding color? I wanted to do that for a while. It's ugly. It's super fucking ugly. It's very ugly. So I'll need to color it. That's the important thing. It'll be very hard for especially people on stream to read. Even me reading, it's very hard. I'll do it off stream. It'll look really pretty when we're all done. All right. So what I wanted to do this stream. How long have I been streaming? I've been streaming for an hour. When I do these streams, I want to come on and I want to talk about the internals of my compiler. That's the most important thing, and then I'll do some coding. Do some recreational coding. But most importantly is getting out my ideas. All right, so what do we need to do in the parser? So check and HIR and parser. These things don't have extensions. So when you click on them, they're a C file. And this is the old parser. And since I don't have feature parity with the old parser and this current parser, I have to cross-reference. So everything I have in this and I don't have in this, I need to copy over and translate. So let's start. So this is in the p-expa, which means parsing expa, and this returns a r-expa, which is the return. And when you're returning, it returns a value, an lvalue, and returns a reference to a block. So that's the block the lvalue was created in. Pretty simple. So let's say you have talk true or false. So expa.value equals LIR lvalue, create an SSA temporary instruction, which contains inst bool literal. Yeah, so what I need to do now is essentially the expa. Let's go down and find it. Where is it? Just here. All right. What do you have that I don't have? So this is the pif. These are highly annotated. I make sure to write a lot. Just about my thoughts, especially for future people and me as well. Alright, so what I did, do blocks here, break expression. So yeah, I wrote a ton here. Returning a noreturn type is involved though, since it requires unreachable control flow. Construct a new block with a noreturn parameter and use that as the expression return. Because that's the only way you could construct a noreturn. It's with a block that never gets reached. And because you can't produce a value of noreturn, it's pretty nice. It's a really nice abstraction. Okay, well, talk do, loop, and let. What would be good to show off some things? Run dev says well-documented code is one of the best things to exist. Yeah, that's right. Especially the Rust compiler. Like you don't even need to go inside the like the Rust compiler at all. It just has docs that would tell you everything. Zaka says, do you detect some naming conflicts on this stage, or is the job it later passes on IR? You mean like duplicate variables with the same name and the same scope? I think you mean that. Well, I do that. I detect every so everything so my whole philosophy is do as much as possible in the parser than you can, right? So I know AST. I'm doing this completely statement based. I'm unwrapping all control flow into basic blocks. And so that I'm doing a lot there, but there's also a lot I'm doing with like variables and stuff. So, what I had in the old compiler, what I had in the old rewrite, well, not the old rewrite, in the compiler where I had when I used the HIR, I had this notion of scopes, and I think I talked about it before how scopes are implemented. But I don't have scopes anymore. How I have them now is this. P-scope entries. This is an array of 256 scope entries. And so this is how it works. You have yeah, let's say you have an array of scope, and then you have an entry 0, which points to the beginning here. Three. Okay, so yeah, so 256 scope entries right here. And in p-scope entry, it stores this. So it stores a name and a location. It has ps local and ps symbol. Don't worry about ps debug reference. That's for that's a really elegant trick that I transformed over. I'll explain it in a bit. Anyway, let's say you're in main, right? Main function returns nothing, does nothing. Main do, and then you define a new function, add. I have to do two. Inc. P+1. Okay, now this thing inc is not a local at all. This inc isn't a local, it's a symbol. So there's an obvious distinction between these things. So this inc here is a symbol because it's a generated function outside and then exposed inside the scope as a symbol. And then v is a local. So it's pretty simple. So inside the scope, you can have symbols and locals. And how it works. So you can go here. All right, there's three functions that you need to be wary about. So p push scope, p pop scope, and p scope register. So when you're calling p push scope, it stores. So here's the scope entries. Here's the length of the scope entries. All this scope stores is the current scope entries length when you're pushing, and when you're popping, it pops the length, one of the lengths off the stack, and resets the scope entries length to that. And I can show you. P scope pop. Yeah, so p push scope. So p dot scope equals plus p dot scope dot len equals scope dot entries dot len. When you're popping the scope, you minus scope dot len, p scope dot entries equals the top of that scope. So you're essentially how it works. Where is it here? P scope register. Yeah. In p scope register, you construct a p scope entry, which can be a local or symbol. And all it does is just append it to p scope entries. And then all p push scope and p pop scope is stores the length of these entries and resets them. So let's say you have you're right here, and then you're pushing to the scope, pushing to the scope, pushing to the scope, and then you push a new one. So now I've entered the new scope, and then you're pushing, and then let's say you leave the scope. This resets all the way down to the bottom. You leave the scope again, and then this resets down to the bottom. So, like I said before, scopes, you don't need to store them because all local references can be identified in the single pass. I mean the single pass C compilers that exist. So I mean this is pretty simple. I'll show you where I use it. Just parser.c and p function. Here, look at that. So I'm pushing a scope, parsing the list of patterns. These patterns add to the scope. I'm pushing a new scope, parsing the expression. I'm popping the scopes. It's super nice. It's really simple. It's the simplest thing in the world. And especially on pdo, so I'm parsing do blocks. It's push scope and pop scope. Simple. How I had it before is I was allocating a tree structure of thingies, and at the end of the day, if you can evaluate everything in the parser, why store it for use later on? There's no need. No need at all. What else I was going to explain? I was going to explain what pdebug reference does. So let's say this whole thing is all in one scope. You zoom in. Let's say this whole thing is all in one scope. So let k equals v. All right, and then let v equals 20. All right, well, there's two ways to approach this. So v could resolve to an outside symbol, so v could resolve to a global, or it could resolve all the way up here. Well, what I chose is, this is an error. You can't do this at all. That's how it is in the V compiler and stuff like that. I think in other compilers as well. Not in Rust. But yeah, so let k equals v, let v equals 20. So a declaration of a variable in the same scope where it has uses is an error. That's an error. That's a complete error. You can't do that. I think it's nice code when you do it this way. So let k equals v. So when you're going to parse, the parser has to search for where v is. Okay, it searches down all the scopes. It can't find v at all. Okay, v might be an outside symbol, and that needs to be resolved by the checker. And then we'll just return the symbol. So you're returning the symbol. And what it does is, when you use it, it inserts ps debug reference. ps debug reference doesn't store any data. It just returns the name. It just stores the name and the location. So what we'll have on the scope stack by here, we'll have a ps debug reference to v. Okay, and then when we get here, it'll check. Okay, do we have any PS debug references that reference v? Okay, we do. This is an error. You can't define a variable with uses in the same with the same uses in the same scope. This is what it does. It's a really nice, elegant guard against this. Now, what I had before in the old compiler is I had this ugly fucking mess. Where is it? In parser? I had this. HIR sim find use. It finds uses in an expression with a name, and this is a recursive function. It recurses over the whole thing. And then here, HIR sim find uses in a list of expressions with a name. Okay, where is this called? It's called here in HIR new var. It takes a parameter, previous expressions. And here, in all uses where you need to create a variable, you need to pass the previous expressions. I do this 9 times. So in p expressions, you need to pass previous expressions. In pproc, previous expressions. Pre-statement, previous expressions. P-loop, p-pattern, p-let. It's a very ugly solution. So instead of going back and searching all the instructions, why don't you just insert it into the list of scopes? It makes sense. It's a very elegant solution. It's just one of those things that you can do. Can I ask a very off-topic question about interning? I use string interning in my compiler. Ask away. In the meantime, find out what I need to do now. Get these side by side. Yeah, just ask. PX, bro. Okay. Everything is interned on a single thread, both identifiers plus string literals. Yes. Everything in my compiler is interned. All strings are interned. I never use const char pointers. I rarely use const char pointers. I'll show you how. Here, okay, LIR PS entry name. Okay, you see this thing here? It's called an istir. It says here, type unsigned int to handle to an intern string. Okay, we'll go to its definition. It's a U32 and istir. Interning can't be parallelized by the nature of it. Well, you could. See, not often will a thread be writing to an interned thing. Yeah, not often. See, what you could do. Okay. So there's 2 ways to approach this. One is you can have a hash map with a lock. It's a simple solution, right? You have a hash table with a lock. I'll go to where I intern on my. It's just a C file called intern. Here, so you're calling sv move, which calls sv intern and just returns a handle to an istir. Okay, so there's here is my hash table. Intern key, interns, char key, this thing. I use stbds. Yeah, so you say for small things it would block a lot, probably. Well, in reality, I mean, there's more operations. You're not like, you only need it when you're creating a variable. You only need it when you're creating a variable. So yeah, only need it when you're creating a variable or a string literal. So I mean, you're not creating that many variables. There's more code than variable creations. It's like a pretty big percentage difference. So that solution 1 is a quick and dirty solution you can do, and it won't even be that bad. All right, there's a second solution though. You can allocate a big whole arena, and then I haven't tested the parallel, but yeah. So you can allocate a big whole. Allocate a big whole arena. So all an istir is an index. So if it's just an index, it doesn't matter what thread is writing to what. It's just an index. So you can allocate this big amount of memory, right? Just assume it holds a bunch of like string data, and then you can pass slices to the different threads, and those threads can hand back stuff. And as long as they're in the same, they're in the same what's it called, thing, as long as they only touch their own region, it's fine. You can still return an I*T when indexing from the whole region. It returns a string. Now, I'm pretty sure there's like some kind of lockless string interning where if there's no I'm pretty sure there's some kind of like lockless thing. If there's no because the only slowness would be when there's hash collisions. So I mean, I don't know. I think you should look up I haven't even looked it up. Just the ability to oh, what was I saying? Yeah, just a hash map. Just a concurrent hash map. I think it's possible. I think there's like some kind of lockless version. Uh, you know, when I rewrite the compiler for bootstrapping, I won't add parallelism because I want the compiler to be portable. When I mean portable, I mean I want to compile this to WebAssembly and run it, right? I want to add a nice add a nice interactive on my blog. I mean, I'm like WebAssembly is like one of my things. I was worked on the V compiler and WebAssembly. I love WebAssembly, so I want to make this compiler portable. Ron Dev says, wouldn't one of the easiest ways to do it without locking to some simple math to delegate to each thread? So do you mean when you try to access the backing string on an I*Stir, you would like check the thread ID or something, or allocate a bunch of like thread local blocks? See, I don't want you can't allocate a thread local block because you want to be able to pass I*Stirs around to you probably won't pass I*Stirs around to different threads, but when they're all dead and you have like the final representation, you probably want to go single pass, single threaded, and those you want to be able to reference those I*Stirs that have been like created by different threads. ID like to basically index thread pool, I guess. Well, I mean, you could probably do like 16 16-bit where it's like thread ID then pool yeah, so a U16 thread ID in a pool. Or you can even make this like a U8 because no one's gonna make that many. Not U48, just to. Yeah, I mean you could probably do this. There's string buffer data plus map. What do you mean by that? But yeah, run dev this thread ID plus pool thing. Not pool. Like IDX. You can do that as well. I think this is probably the quickest solution. But you also have to pass it the memory box. It can't be a thread local because you eventually want to access it. But that's the quickest way. I think that's the quickest way. Not all the time. The only point to interning is for quick comparisons. You want really fast comparisons. So, I mean, if you're not, it doesn't matter how fast it takes to access. You just need to do fast comparisons. So Zach says, I mean the structures needed are a buffer for string data and a hash map. Yeah, that's what it's needed. That's what's needed. It's just the hard part of what is it called? Parallelization, and you're trying to access it. Splitting them all up into different sections is a pretty nice idea. If you join the Discord, after stream, if you guys have I might take a shot at implementing it maybe. I currently copy everything into a linear buffer for label lookup. Oh, so you copy you use like a then I assume they're null terminated. You just put everything in one long arena for a long strip. Yeah, that's fine. That's perfectly fine. What I do right now is just malloc. I could use your method. Eventually, I want to use your method in the compiler later on, because there's a lot of places in this compiler where I could do arena allocation. Anyway, the parallelized hash map is nice. It's pretty nice, but I won't add it in my new compiler. When I bootstrap it, like the final bootstrapped compiler, it'll be as portable as possible. That means no threads. That means no threads at all. It'll be fast enough anyway. Plus, there's certain things that you can't do parallelized. I can't think of much on the top of my head. What I can think of is like you can only parallelize between certain functions. Just quick, could you explain when calloc would be preferable to malloc? Ooh, see, the thing is with calloc is, oh man, so calloc. All right, here's calloc. So void malloc with a size, and calloc is a number of members and size of each member. So you'd use calloc with arrays. Let's see the semantics. Function allocates memory for an array of nm elements of size bytes, and each returns a pointer to the allocated memory. The memory is set to 0. If nm both size is 0, it just does what malloc does and returns a unique pointer. Well, not a unique pointer, just a pointer with size 0. Okay. Yeah, so calloc is basically this, malloc nm.size. So, I mean, calloc is essentially equivalent to mallocing and then mem setting was 0. Could you explain when calloc would be preferable to malloc? It's just a function. All calloc is just allocating zeroed memory, right? You could do the same thing with malloc with a multiply and a mem set, right? You'd want to multiply the members. It's nice for allocating arrays. I personally have never used calloc as much as malloc. I don't think I've ever used malloc in a serious C project. I've only ever used I don't think I've ever used calloc in a serious C project. I've only ever used malloc. Very rare that I use calloc. You can use it if you want. You can use it if you want. It's pretty convenient. Now, what I'm a bit iffy about with calloc is that memory zeroing thing. I don't know if that's a part of standard. Calloc in the standards. Let's see standard. Okay, wait, where are the CPP reference? I love CPP reference. Favorite site. Calloc. Because it has these... initializes all bytes and allocated storage to 0. Okay, well, this is in the C standard. I've seen certain platforms, maybe freestanding or not. I think there was something on Android or something, right? I've seen calloc functions in the wild that don't initialize things to 0. That's why I'm iffy to use calloc. Like, I just don't want to use calloc. I mean, it seems like, I mean, if you look at the C standard, it's pretty portable. But in my head, it's like, I don't know, right? I don't know, because I've seen like issues before. Use calloc, use malloc. Doesn't matter. Doesn't matter. I don't think there's a difference, except for the mem setting. I use calloc for string reversal. To be clear, I had to return a char pointer, so I couldn't reverse in place. Oh, you mean so the whole thing is oh, that's pretty smart. It's like well, you mean like calloc to automatically have the null terminator exactly where you want it? I mean, even in that situation, I'd still use malloc and then manually set the null terminator. That's error prone. A compiler would have to be really good if they were to optimize that. All right. I'll see if I can talk and work. Now, what I want to do now is loops. All right, run a new case talk loop. All right, and that loop can have an optional label. So it's just this. Okay. So it's pretty similar. P-loop. I bring the parser on this side. The old one. Oh wait, no, that's not the old one. This one's the old one. Alright, so all it is, wow, that's the simplest thing in the world. Rondev says, I only populate the characters I need. I calloc length +1. I don't know if that's the best way, but it's cool. Yeah, it's one of the ways to do it. It's not the fastest way, but it's the most less error prone way. It's it's not prone to errors at all. It's pretty foolproof. Okay. So, what does it take? Expert config. Okay, I want to take that as well. That's important. I'm gonna put a to-do here. To-do. V equals. Okay, it's very rare that I use these multi-lines, but I just can't. I'm not bothered to add these things. I'm just writing a note to self. Alright, because I want to allow this. Okay. Alright, p loop. CFG. Okay, simple. So we grab the lock, the location of the first one, and we add a block. So block ID, incrementing that, and we're inserting a new block. So the when you call break, you can find it. And so always break true, and then our expert equals p expert. Just calling that. It's p stomach. All right, good. Okay, how is this gonna work? Okay, the best way to do it is go over here. This is where I do all my stuff. So much stuff. Yeah, split control for using a goto abstraction. Okay, what do I need to do? Okay, let v equals loop with nothing. Okay, let's just try and lower that. Entry block. Go to loop. Go to loop. Percent 0 equals tuple, empty tuple. And then discard. Okay, and then loop end is no return because we literally can't reach here. And okay, that means v will have a type of no return. Okay, lowering. All right, now if we want to lower this, let v equals loop do brk with 20. All right, entry. Go to loop. How does the how is this gonna lower? I think it should be fine. Let me just copy one of these. Think. Okay. It'll be do. It won't break out of the do. Yeah, loop exit. Which is a 1 I32. Okay. Equals 20. BRK loop exit with %0. Not loop, goto. And it would need to produce that value. So it would have another one. Loop inner. Which is no return because you're breaking out. Because you're breaking out of the whole thing. And then you want to just go to loop. Simple. And then this can be trivially optimized. And yeah, because you need to produce the value of break, and then in here you go to the loop. Simple. I mean, yeah, this is well formed. Okay, let's do it. So loops can always be broken too, and they always need a top and a bottom. So we need to create one. So let's go to, let's put the do block code on this side. Okay. So we need a LIR reference to block loop repeat. So this is the header loop entry, and we need a loop break, loop exit. So that means the break block is this, and the repeat block is that. Okay. Loop. Okay, first we need to make sure that this block goes to entry, which means we need to join them together with a LIR block terminator. Yep, fill it in. Okay, good. And then we can finally pass the loop entry to the block. Loop repeat. All right, and then expression will return us a block. So we need to do expr.block needs to jump to loop exit. And then we just return loop exit. Okay. Now, loops here can return stuff and not return stuff. Actually. No, loops always return something. They either return nothing, which is an infinite loop, or they return something. Wow, that's the beauty of like functional abstractions in a functional type system. I love functional type systems. Everything has a value. Even divergent control flow, like noreturn control flow, they have a value. Such a nice abstraction. Like I love functional type systems. Okay, well that simplifies a lot of things. So so we need to do term LIR. The loop block has to go to the loop. Zaka says Rust falls in the same category. Yeah, it does. It does fall into the same category. Rust hasn't stabilized its noreturn yet. The bang noreturn. So it's a bit of a shame, but that is Rust does fall into that same category. Okay, any languages, any languages, no, any language that has block expressions and like unreachable, which evaluates to like an actual value. Any language that has block expressions and unreachable, I mean, you basically done enough for a functional style. Just the ability to have void as a value and no return control flow as a value. I mean, that's great. I mean, you've really done enough, right? No more. Good enough with your functional implementation. So these languages like Rust and Zig, I mean, they've got it. All right, so loop, the end of the block needs to go to the top. So it needs to go to loop entry. And then loop exit. Loop exit always has a value. What does no return mean? It means no return. Okay. No return, exclamation mark and no return are the same thing. No return is just like in Zig. So Zig can have no return. And this is basically a no return. In functional programming terms, this is called the bottom type. It means the bottom type means that you can't construct a value of it. It is impossible to construct a value of it. I'll explain how you could create a value like that. And here, let v equals loop. Loop takes in an expression here and consistently loops. So if you want to use loop effectively, you want to break with a value, right? Because you're breaking out of the loop. Okay, so loop always evaluates to a value, but it never breaks out of the loop. So what does it return? It doesn't return. It can't return a meaningful value. You'll never be able to inspect the value of v because it'll always be looping. So what it returns, basically in its type system, is the bang, or the bang operator, or the no return, or the bottom type. What it means is v has the type of no return. So that means that you'll never be able to read the value of v because either your program will be in an instant loop or you can just like return out of the function. All right, you'll return out of the function. I mean, it's like, yeah, same if panic and exit happen. That's the exact same inside the block. Divergent control flow. You will break out of the whole thing entirely. That's what no return is. It's a great functional abstraction. It's amazing. It's great. It's like one of the best things in the whole world. The functional gods gave us. Okay, so expr has a block, so you want that to bench the loop entry unconditionally. So LIR block terminator. Wow, thank you for filling that in. And then what I want to return, so loop exit always has a value. So in here, loop exit always has a parameter. So Ron Dev says no return is technically a value assigned to the variable no. Yeah, I mean technically in the type system, it's not even a value. It's not even inspectable. See, t equals this, right? This is a value. It's inspectable. You can read it, right? You can go here and be like, oh, what is it? Right? You can inspect it. But the no return, you can't even like do anything meaningful. It's not like your program past here doesn't make sense. It's you can't read v. You can do this though. Let k equals this. Because the bottom type is compatible with all other types. So k evaluates to an i32, right? You can do that. I mean, this makes perfect sense on the eyes of the type checker. The type checker will see bottom type plus an i32. Okay, they're compatible. This is an i32. The type checker will see this and go, okay, that's fine. But I mean, it makes sense with the functional programming world. But the reason why it's able to like coerce these things is because like you can't actually read the value. It'll never reach here. It'll never reach here. It's not technically a value. It's more like if it ever gets here, it's undefined behavior. It's like you'll never be able to read v. You'll never be able to read t, which is why I really like a way to construct a no. The only way to construct a no return or a bottom type in this IR is by creating a basic block that has a parameter that is noreturn, right? And if this basic block never gets, you have to make sure this basic block never gets gotoed, jumped to. And this makes sense. You can delete this code. You can delete it. I mean, if the checker looked at this, it'll be like, okay, loop inner has a parameter of no return. No return can't be produced under any circumstances. Delete the whole thing. Right? That's a perfect transformation. And then like, yes, I mean, what the checker would do is delete this, delete that. And oh wait, go to exit. Okay, delete that. And then return that. I mean, that's what the checker could do. But it's a really nice functional abstraction. I love the idea of a bottom type. Okay. Loop break. Loop exit always needs to return a value, so it needs a loop argument. So SSA block new arg. Yeah, new argument. So it takes a procedure, its current block, so loop break, so it gets to the end. Type bottom. And its location is alloc. That is the loop. Okay. So it has an argument. Well, no, it doesn't. It's only the bottom type if it never returns a value. I'll need to know if this ever gets broken to. This is what I want to store. Okay, so in the list of blocks, p block t, I want to store bool is brk. Okay, so if just with loops. Okay, so the whole point of loops is if since the type system, or like since the compiler can see that this loop has no breaks out of it just by looking here, it doesn't even need to inspect the IR. Like this loop has a break in it, which means it may return something, which means it can't be no return. It says no loops in it. It's an infinite loop. It must be no return. So I need to make sure that this never gets broken to. So we can do that. We're doing this is brk. So what I want to do is in here talk break. Here's block ID. P blocks block ID dot is brk equals true. We are breaking here. Okay. We do type infer LIR local t. Okay, and if at the very end we don't, at the very end it doesn't have a, if it doesn't have a break to it, we just need to return no return. Without block as expression switch / match become almost unusable. It's main benefit I see. You mean like oh yeah, like block expression switch. Not a great fan of implicit returns anywhere, but matching is great. No, in the loop, the only reason why the loop is returning no return is because it never has any breaks to it. The compiler can see that this is an infinite loop. But you say implicit returns. Well, if you're using a do block, you know for a fact what you're getting into. So, the last expression is always the value. If you're doing something like this, let this equals this, it'll ignore the last expression, though, which is a good thing. Yeah. Oh yeah. That's sorry. No, that's right. Yeah, having expression switch and match is great. It's like one of the best things. Like, it's good to have. Okay. Loop break value, so we can either return type infer or no return. Yeah, no return. So what we do is do this here. fp blocks len dot is break proc dot locals loop brk value type okay, it does not have a break type Zaka says, would it be acceptable to limit which blocks can implicitly return? Or that breaks the language you feel like? Opinion-based choice mostly. Okay. You mean like which blocks can implicitly return? The only thing that can implicitly return right now is the do block. Like, I mean, the only thing that's like slightly ambiguous is the do block, right? Because the last expression will always be used. How they do it in Rust is if there's no comma, or not comma, if there's no semicolon, that returns, else it's no return. Not no return at bottom. I don't think there's any issue with having these things return. Also talking, yeah, you mean like well, that's the only thing I can think of, the do block. There's nothing else. I mean, even if you have like a match something, you have like expert cons expert. I mean, you already know that this is going to be returned. I mean, you can tell that's not ambiguous at all. Which blocks can implicitly return? Oh, so you mean like being able to tell do not to implicitly return? The only way to do it is, as far as I'm concerned, the only way to do it is by passing an up value. Okay, what if C return from switches only as implicit return? As only implicit return. That's the example. Okay. Let's see example. Because in a switch statement, I'm assuming C, so there's going to be a lot of not imperative, like a statement-based code. So there's statement-based code in the arms of the switch, right? And you don't want to be returning that. If you just have a switch just like this, blah, 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 blah. This is just some fake code. If you're never using a variable, you can just ignore it, and then the optimizer can just handle it. The optimizer will be able to handle it. I mean, it may implicitly return, but there's no way to inspect the value unless you assign it to something. Yeah, I don't think it seems like a non-issue, especially when you can just ignore. But what might be an issue though? Let's assume that you're calling a function, right? Function. You're talking about lang design. Yeah. Yeah, like you want to let the yeah, if only some blocks could return implicitly. See, yeah. This is a functional programming language, so everything basically has to be an expression. But there's one case where things might be an issue. So I'll just show you now. Okay, let's say you have a case, right? You're calling a function, and let's assume these are functions, right? Function func3, right? And assume this returns an i32, this returns nothing, this returns a bool. Okay, and then this will cause an error. the type checker will be like, okay, this is returning this is returning that, and this is returning that. There's very obviously like these things aren't compatible, so you're performing an effect, but it'll cause an error. If you're doing this, this is very much malformed. You can't do that. But I feel like the checker would be able to see like, okay, you're ignoring the value. That means you're ignoring the returns of this. It would be nice. It would be nice to like signal to the switch that to ignore. One of the good things, one of the good ways to signal to ignore would probably be like a match on nothing, because in the HIR, so the older one of the compiler from a couple days ago, you could do this. Yeah, if like I'm gonna make every single thing in this language return implicitly, so it's everything's gonna be expressions. But if that ever gets ambiguous, I'm gonna change that because I don't like ambiguity. Okay, so p blocks is break, so it doesn't break at all. Type bottom, so this is an infinite loop. Okay. So the return value is the loop break value. So expr block goes to loop rep, and then loop exit. Where's loop exit? Loop break. Oh no. So all it is just our expr t equals the block is a loop brk. The value is a loop break value. Okay, why is this having an error? All right. Unused. Okay, simple. Let's see if it works. Whoa, what was that? JMadH1III. Sorry, I butchered that. Hi, welcome to the stream. Okay, let v equals, okay, there's no infinite loops. Just loop infinitely. I want the value. Alright, let's see what it does. Did we do it? Okay, we're in the go. Did we do it? Okay. So, pattern. Go to loop entry. Loop entry.2. So that's right. So we're now in the loop entry. 3 equals this tuple thing, because that's the expression here, and then go to loop entry. So it'll go here, it'll jump here, it'll loop forever. This whole thing is looping, looping. And the computed value of that, since it's an infinite loop, it must be a no return. So here, loop.exit 3, this is completely unreachable, but it's not malformed code. So this makes sense from the eyes of the type checker. Yeah, so loop exit has no return, and since this loops forever, it never gets here. This is well formed. You can return that no return, and then it just returns ret true. Perfect. That's perfectly. That's super nice. And then what we can do here is just brk 20 immediately. See what the checker does now. Not the checker. The parser. Can you add ANSI color to jump labels if it's fast to do? After this fix, I just implemented loops. I feel like I'm going to close the stream. I don't think I'll do it on stream. As soon as stream's over, I have some time before I go to bed. So as soon as stream's over, I'm going to implement that for you. For both of our eyes' sake. Alright, let's see. So pattern 0. Oh, yeah, sorry, man. This is probably really fucking annoying to read. Yeah, sorry about that. Yeah, so go to pattern 0. I'm gonna go here to pattern 0. This is just the expression here. It'll go to the loop. It'll go to the loop entry. So this is the loop entry. %3 equals 20. Now it'll go to loop exit with %3. Then here, loop exit 3. Yeah, loop exit and then %2, and then ret %2. I mean, that's fine. All this is just going here, here, jumping here, here, exit. And then here, this .l4, label 4, with this bang, that's the value of this BRK right here. And you can just, it'll jump here. That makes sense. Yeah, so there's like a loop here, and then this returns just here. Anyway, perfectly well formed in the eyes of the checker. Good. Loop forever. Great. All right, let's make this commit, and then I think I'll go to bed. I think I'll end stream is what I mean. Okay, parser or man, I gotta figure out what I want to name this language. It's like I'm gonna be done with it, and I won't even have a name yet. Okay, what did I do? Loops. All right, what stream is it? Stream 11. LIR 10. Parser. I did not touch the LIR, just the parser. Implement loop. Done. Look at that. Would it make sense to require some sort of termination condition for loops? To require that and force that, I don't think I want to force that. Okay. Composer says, "Hey, I just wanted to say I appreciate your YouTube content." Thank you. Thanks. I'll be up with more since I talked a whole lot during this thing. It'll be nice to talk about just my thoughts. So I talk about a lot of my thoughts here on the stream, so I'll probably clip a couple. All right, back to your question. Zaka, often people just hang the programs accidentally. Okay, so yeah, see, thanks Copilot. You are the dumbest fucking AI in the whole world. Okay, let v equals loop infinitely, and then function. Okay, so let v equals loop. This will obviously evaluate to no return. Okay, in the checker's eyes, when it gets here, it'll raise an error. You go like error. Reachable code. It makes it more with the check. Oh, fuck off. Okay, with the checker showing these errors here, error unreachable code. It's I don't think it's very ambiguous. If people want to do an infinite loop, and obviously you can obviously you'll be able to know that an infinite loop is infinite just by it having no breaks. Also, the checker might also do this. V here. Error. It'll do it on the assignment actually, because you're assigning a no return value to a local. It'd be like error unreachable code. The thing is, if you could somehow create a no return, the checker will warn you in like multiple places. It'll warn you here when you're trying to assign a no return to v. It'll go error unreachable code, and then it'll go down here. You try and call the function error unreachable code. If by any way you could create a no return, the checker the compiler will just complain. But even things like yeah, so you say require some sort of termination condition for loops. If people want to do an infinite loop, I don't think it's very ambiguous. I think they'll be able to tell where an infinite loop is, especially because it's only an infinite loop when there's no breaks. Now what I want to probably add. Oh man. Okay. Let v equals true. let k equals loop do if v brk with 20, else infinite loop. So in the eyes of the checker, is k neither do 2 or is k no return, right? I say it should be actually no, wait, no, this is not right. Here, if you look at this, let v equals false, let k equals loop do if v break 20, and then k. What's the type of k, right? Because I want to do conditional constant propagation all the way down. So maybe even the presence of breaks in a function, even the presence of breaks may or may not constitute it being no return or not. That's the thing. It's like control flow based type system as well. That's what I want in this language. So I want this to be possible. I want k to have the value of no return. I want it to be statically determined that k is the value of no return. You can see here, let v equals false. Let k equals loop do if false, brk 20. Okay, there's no breaks. And then k. So, oh man, that'll be a hard problem to solve. Yeah, I'm gonna write that thing down. I'm gonna write this thing down. All the way up at the top. You go all the way up to the top. This is where I have this. Conditional loop types. This is important. Okay, now I have to do 2. I say this is possible. Now, we'll probably need to remove... Oh, we'll need to do type checking and this. I say this is possible. Hard because it would... True. Who knows? Maybe I'll think of some way to do it, right? But that's for future me when I'm done with the parser and I'm onto the checker. But that would be nice to implement. Having it be able to just conditional const prop and find the type. Okay, but all right, I think that's it. All right, did I push the commit? I didn't. Okay, well, I did. All right, well, I think it's over. 2 hour stream. I talked a lot. I didn't implement much, but I only care about the talking. So, thanks for showing up. If anyone has any more questions, I'd be happy to answer them. Zaka says you could generate typed IR. Yeah, no. So no, that's right. You can generate another step, but yeah. See, the whole reason why I wanted to remove an AST is because I don't want to make an AST and then make the control flow graph, right? I just want to have the whole language the whole language in one IR, the one IR to rule them all. That's one of my like just things that I want to have about the language. So this IR is typed. Plus it wouldn't solve that problem. Generating typed IR wouldn't solve the problem because I need types to do conditional constant propagation. So I'll need to merge the type checking and conditional constant propagation. I'll need to merge I need to merge like all of these stages, I think. I need to merge this and this, but then I also need to remove dead code. Yeah. It's this thing's hard. It's merging 1 to 5. It's a very complex problem actually. You know, maybe I'll think about it. Right? But I'm pretty sure I don't. This is something what is it? This is something I probably can leave out, right? Zakazaka says, can't they be done in parsers on the same IR? Now, propagation of facts, range checking, and conditional constant propagation. Conditional constant propagation is the kicker here. Because if you conditional constant propagation, we'll be able to insert this here. And then remove this entirely. Now, you say merge them. The reason why, I mean, if you don't merge them, you have to run them at multiple times in the different things. So there's a very specific and really nice algorithm. It's like a work list lattice thingy. I'll link a video in the description. It's by this really nice guy. It merges conditional constant propagation with dead code elimination. So that means I can just run through it all in one go. I could put them in different parsers, but then it'll be like I don't know how to explain it. It's like you'll never reach the end goal. What am I trying to say? You can run them two at once. Yeah, so conditional constant propagation and dead code elimination, there's an algorithm so you can run them together. That is what I want to do. This whole thing, this number 5, propagation of facts, range checking, conditional constant propagation, language-specific optimizations, and dead code elimination plus region analysis. Those are all combined in one thing. Most of these things you get for free with conditional constant propagation. So you get all of this for free. The only thing important is this thing. You get the rest for free. But you can't split them. It becomes what's the word? It's like impartial. It becomes partial. Like you won't be able to eventually end up at the ending. There's like some it's like it is better when they're combined because the information works in tandem. If they're split, you probably won't get the best possible optimizations. You could run them multiple times after another, but it'll diverge slower than if you just ran them both at the same time. That's my best answer for you. Yeah, it'll diverge slower. Okay, so I think that's it. If anyone has any more questions, I'll be happy to answer them. But I think that's it. That's it. Let me just close. Bring this over here. Yeah, close. What time is it right now? 2. Oh, fuck, it's 2 a.m. Oh, man. Alright, well, I gotta go to sleep, so. Alright, well. Thanks, guys, for showing up. It's a good stream. Yeah, good night. Good night, everyone.